Hi everyone. In this lecture, which will take a couple of videos, it's an addendum lecture to the actual course. I'm going to recap some results, basic results we need from Galois theory. In particular, in this video, we are going to talk mostly about normal extensions. And again, this is not part of the course. Technically, you are all assumed to know Galois theory, but just in case this is a video that you may want to see, or series of videos. And also, I also give some examples that are more related to our course. Usually, you don't see such examples. Usually in Galois theory, you see examples from extensions of Q. And I want to talk about extensions of the rational function field. So yeah, so hopefully that will help. And mostly I'm basing my presentation on Richard Borcherd's Galois theory course. It has many courses. Richard has many courses in his YouTube channel, and you're welcome to look at it. Void is quite addictive. Consider yourself warned. Okay, so let's start. Okay. So, informally speaking, a normal field extension is, well, as in everything that we're going to talk about today, it's an algebraic extension. Right, the transcendence thing that we are looking at in curves is not going to appear here. We're looking at the algebraic part. So we're only considering algebraic extensions. And informally, we say that an algebraic extension is normal if whenever you take a polynomial with coefficients from the lower field K that has at least one root in L, well, assuming that polynomial is irreducible, then all of its roots are in L. Right, so like the kind of conjugate class of roots of f is either contained completely together or not at all. But of course, this is somewhat informal because what do I mean the roots of some polynomial, right? F doesn't necessarily have a root in K or in L, and if it has a root in L, then technically it can have some roots in L and some roots in other field extensions of K and so forth. So the right way to define normal extensions is as follows. So an algebraic extension, again, all extensions are going to be algebraic. L over K is normal if every irreducible polynomial f of x with coefficients from K that has a root alpha in L, that makes sense to say, factors to linear factors in L of x. Right, and this is the way you formulate all of its roots are contained in L. Okay, and of course, reducibility is critical because I mean, it could be that one component has a root and therefore all other roots should be there, and another component has nothing to do with the first component and so forth. So that's the right definition. Although it's maybe not necessarily be the best way to work with the definition. So this is why we have the following theorem. It's a basic theorem in Galois theory that we are going to prove, just to remind us of things. And it just gives different characterizations of normality. So let's say that L over K is an algebraic extension. And here I'm assuming, and that's what we are going to do for the course, is that L is contained in an algebraic closure of K. So what's going to happen all the time is when we are working with algebraic extensions, we are going to take the smallest field, in this case K, and we are going to consider fix an algebraic closure of K. There is only one algebraic closure of K up to isomorphism. An algebraic closure of K, so we denote it by K bar. And then a known result tells you that actually every algebraic extension of L, even if technically it's not of K, even if technically it's not contained as a set in a K bar in algebraic closure, there is an isomorphism that embeds this algebraic extension to K bar. Right? So the picture is, if you have K and you have K bar somewhere at the top, and then there is some algebraic extension L of K, which doesn't care about K bar. Maybe you got it before you kind of decided to consider that particular way of presenting the algebraic closure. When there's always a map, an isomorphism, an embedding, which takes L to some L prime that is contained as a subset in K. So in K bar. So this essentially means that we can always assume we are working within K-bar. So no isomorphisms floating around. Every inclusion is a strict, like set theoretic inclusion. And it actually goes further. It tells you that even if L and M, if you have two extensions of K and one extends the other, so L extends K and M extends L, then that way of embedding M and L in K-bar respects this structure. Okay, so really you can actually assume that you're working within K-bar because everything you care about, which is extensions and so forth, is going to kind of be mapped nicely within K-bar. Okay, so let's erase this. Okay, so going back to the theorem, say we have an algebraic extension and it is already contained in K-bar, then the following are equivalent. So the first is saying that L over K is normal. And here we didn't really need K-bar because we kind of avoided talking about the roots of alien extensions just by talking about the linear factors of the polynomial of the irreducible polynomial corresponding to alpha and so forth. Another characterization, which is somewhat kind of less known, I think, or less used sometimes, but it is actually a very easy characterization to verify, is that L is the splitting field of some set, any set of polynomials, or not necessarily reducible, with coefficients in K. Okay, so there is some set of polynomials, could be any set, I could be index set of any elements. Alpha is like just a general, it's not an element, it's just a name for the polynomial. So this is usually easy to verify. It's hard to work with this to verify. And so this is the splitting field kind of describing it. And the third way of characterizing normality is with respect to automorphisms of K bar over K, right? So what is an automorphism of K bar over K? So these are precisely the automorphism of K bar, and this is why it was nice to kind of fix K bar ahead of time. That acts as the identity on K. So they fix every particular element in little k. Okay, so the third characterization tells you that every automorphism of K bar over K maps L, which recall is a subset of K bar, to L. I mean, usually an automorphism will map L to some other subfield of K bar, but normality tells you that it's closed in that sense. So the automorphism just sends L to L. It's not identity on L, of course. It's identity perhaps only on K, but as you know, the image of sigma on L equals L as a set. Okay. Good. Okay, so let's prove this theorem just to kind of remind ourselves of the elements that appear in Galois theory and just for fun also. So let's start with 1 implies 2. So I'm going to assume that L over K is normal in the sense that we defined it. And we are going to show that L is the splitting field of some subset of polynomials. And actually that's quite straightforward because, well, for every alpha in L, consider the minimal polynomial of alpha over K. So F alpha is as coefficients in K. So that's an irreducible polynomial by definition. It's the minimal polynomial. Then consider the following set of polynomials. So for every alpha in L, gather around also F sub alpha. Right? This is a subset of polynomials. And so we know that L over K is normal, and we want to show that L is the splitting field of some subset of polynomials. So that's the subset of polynomials that I'm working with. And this is why kind of the suggestive notation of alpha appearing here. But never mind. So you look at this set of polynomials. The splitting field of this set of polynomial clearly contains L, because right, every F alpha has one of its roots. Alpha has one of its roots, and all the alphas together form the entire L. So this is definitely the splitting field of this set of polynomials contains L. And on the other hand, because L over K is normal, we know that each of these polynomials splits completely within L. So we get an equality between this splitting field of this set of polynomials in L, which is what we wanted in 2. Good. Now let's move on to in place 3. So now I'm assuming that L is a splitting field of some set of polynomials, and I want to take an automorphism and an element in L, and want to show that the automorphism sends that element also to L. Right? So you fix an automorphism of K bar over K, and you fix alpha in L, and at the end of the day, you want to prove that sigma of alpha is also contained in L. So let's consider the minimal polynomial as in here, f sub alpha of alpha over K. Now, by 2, from here, we know that f alpha splits to linear factors in L of x, right? Because it's a splitting field of some set of polynomials, and actually kind of according to also 1, we know that it's also the splitting field of this particular set of polynomials because of the proof of 1 implies 2. So we know that f sub alpha is splits into linear factors in L of x, and I claim that one of these linear factors is x minus sigma of alpha, right? And the way to see that, that's the kind of the building block, one of the building blocks in Galois theory is looking at how the automorphisms act on polynomials. So, right, so you know that f of alpha is 0, so let's start reading it from here. F alpha is 0, so sigma of f alpha is sigma of 0, which is a 0, because sigma is an automorphism. On the other hand, if you write f explicitly with its coefficient, where the coefficients are coming from K, then you know sigma acts on the sum. It's an automorphism, so it goes through the sum, and it acts on Ci times x to the I, and it's an automorphism, so it's really, right, so it's really, maybe I should have written it here. It's the sum over I of sigma of Ci x to the I, which is the sum over I of sigma of Ci sigma of x to the I, using the fact that it's an automorphism with respect to multiplication also, it's a field automorphism. Now, sigma of Ci is Ci because sigma is an automorphism of K bar over K. It acts as identity on K, and these are elements from K. So that's why you have what's written here. I also pulled out the I, as you can see. Again, because the sigma respects multiplicativity. And from here, you can say that this is just the evaluation of f on sigma of alpha. So overall, you see that sigma of alpha is also a root of f. These are the conjugates. It's also a root of f. And so when you factor f to linear factors, one of the factors will be x minus sigma of alpha. Right? And because the factorization occurs in L, we know that sigma of alpha is in L. Good, so that's why 2 implies 3. And now we want to prove that 3 implies 1. And for that, we will need to remind ourselves of something. This lemma that tells you the following. It tells you that if you take an irreducible polynomial, there is no L now, just K. And you consider an irreducible polynomial over K, that has 2 roots, alpha and beta in K bar. These are the conjugates because it's irreducible. Then you can always find an automorphism of K bar over K, which will map alpha to beta. Right, so conjugates in the sense that, so alpha and beta are conjugates here in the sense that they are roots of the same irreducible polynomial over K. And what I'm saying here is that there is always an automorphism of K bar over K, which maps conjugates to one another. Okay, the proof is short, but it's insightful. So we know that both of these fields, and I'm only going to sketch it, you'll see why. Both of these fields, K when you're joining to alpha and K when you're joining to beta, both of them are isomorphic to this field, where you take the polynomial ring in X and mod out by the irreducible polynomial F. It's important that it's irreducible, otherwise you won't get a field. Right, and the reason for this isomorphism is because you can look at the map that sends a polynomial to its evaluation at, say, at alpha. In this case, it will be beta, but at alpha. And then you can show that the kernel is exactly this ideal. And the range in everything. So by the forced isomorphism theorem, you get this equivalence and also that equivalence, and therefore there is an isomorphism from this field to that field. And the part I'm not proving, because it will take 10 more minutes, is showing that you can extend this isomorphism from K alpha to K beta to an automorphism of K bar over K. Right? You want to extend it. You don't want it to act only in K alpha. You want it to act on the entire K bar. And you can do that essentially because of properties of splitting fields. But there is a way of doing that. So that's why it's a sketch, really, because I'm not doing that. But having done that, we are essentially done because we want to prove 3 implies 1. So we assume that every automorphism maps L to L, and we want to show that L over K is normal. So to show that L over K is normal, I'm taking an irreducible polynomial over K, which has one root in L, at least one root in L. So f of alpha is 0 and for some alpha in L. And I want to show that all other roots of this polynomial are also in L. So let's take another root of that polynomial. Let's call it beta. And you see that's why it's really nice to have K bar, because you can always pick all the roots from this algebraic closure that you fixed. So, right, so you take a beta from K bar to be any other, potentially the same root, but it's more interesting if it's some other root. Now, by lemma 3 that we just proved, there is some automorphism sigma of K bar over K, which will map alpha to beta, right? And so beta is sigma of alpha, but per our assumption, sigma of alpha is in sigma of L, and per our assumption, sigma maps L to L. Any automorphism. So the automorphism that we also constructed maps L to L. And that puts beta in L, and we are done. Good, so that's the basic result we have for normal field extensions. And for example, as a corollary, we know that a degree 2 extension is always normal. From 3 onwards, it doesn't work, but degree 2 extension is always normal. And the reason is as follows. So you can take any alpha that you want, which is NL not in L and not in K, and consider its minimal polynomial. That minimal polynomial is going to have degree 2, because the extension is of degree 2, and the minimal polynomial can have degree at most degree extension. So if it has degree 2 polynomial, you can write f of x as, you can make it monic, x squared plus ax plus b, where both a and b are in K. And when you factor it in K bar, you can write it as x minus alpha, that's your alpha, times x minus its conjugate, x minus beta. But looking at these two and comparing coefficients, you can see that beta, you can write beta as minus a minus alpha. Right? You look at the coefficient of x. So here it's minus alpha minus beta, and here it's a. So good. So what do we know about beta? So initially beta was taken from K bar, but we know that alpha is in L, not in K also, but alpha is in L, and A is in K. It's definitely in L. So this thing, which is beta, is also in L. So what you showed is that this polynomial splits completely, namely L is the splitting field of F, because it's a degree 2 extension, and F is of degree 2. And by the maybe second property here, which I told you is easy to verify, you know that L over K must be a normal extension. Right? It's quite a strong result, because you just took and checked one polynomial of degree 2, and you know that all polynomials now that have one root, all irreducible polynomial, one root splits completely, just because of that one polynomial. Good. So that's the thing I wanted to talk about, but let's try to do an example. Let's revisit our ongoing example and kind of play with it and see how the things you saw in Galois theory are related to what we are doing, which is mostly working with function fields rather than the examples that you usually see in Galois, usually you take some Q, and maybe you are joining to it a third root of 2 or something. And it's classical result showing that this is not a normal extension because the polynomial x cubed minus 2 is irreducible, but the other two roots are complex, and this is contained in the reals and so forth. So these are the kind of examples that you usually see, and I want to show you examples that come from our in our settings. And again, I think I kind of maybe played with it too much, and the examples that I'm going to show may have a much simpler solution and so forth than what I came up with, but okay, let's see that. So let's consider our ongoing example and set our and match the notations that we used in these slides. So in our example K, the smaller field is the rational function field over some field F, say finite. I think of it as a finite field, and L is obtained by, it's this field, it's obtained by adjoining to K essentially a solution to this equation, or alternatively, you mod out K of Y by this ideal, and this ideal we show actually it's irreducible in K of Y. Actually, we show that this is an irreducible polynomial in over K of XY, like in the polynomial ring in two variables, and because it is monic in actually both X and Y, you can show that it means that it is irreducible also as an element here, namely where you are allowed to use rational function if X and only polynomial in Y, and vice versa. But you can just check it and see it by itself. Simple example. So this is irreducible, so this is indeed a field, and it's a degree 2 extension, right? Because Y is of degree 2 here. And so by the previous corollary, we know that this extension is normal. The fun part will start now, where we are going to consider things in the other way around. So it's the same example, but viewed from a different perspective. So here now, K is going to be f of Y. So we adjoin Y first, and then we adjoin X. So namely, then we define L, so K is different. Then we define L to be the ring of polynomial over K in X, modding out by this, which again is irreducible over K of X now. And I wrote it a bit differently. You see, here I wrote it like Y squared minus those X's, and here I wrote it as the X's minus Y squared, just to, like, psychologically, it's easier to look at that and see that these are the variables and this is the constant because it comes from K. Okay. So now K over L these new K and L are now actually, this extension is of degree 3. And there are extensions of degree 3 which are not normal. And what we are going to try to do in this example is figure out whether this extension is normal or not. So let's look at this polynomial that we are kind of extending K by. So this polynomial, if you are going to factor it in the algebraic closure, you can write it as x minus alpha, x minus beta, x minus gamma. And what do you mean by algebraic closure? Right, so I mean the algebraic closure of K. Right, I mean this is a polynomial in K of X. So you may need to take extensions of K in order to find the kind of to locate these roots alpha, beta, and gamma. But K itself was the rational functions over F in Y. So really what we are talking about here, alpha, beta, and gamma are coming from here. And what do you have here? What do you mean, like the algebraic closure of the rational function field? Right, so in the rational function field, you have like Y and 1 over Y plus 2 and so forth. And in the closure, you add things like square roots of Y and things like that, right? So you essentially add like radicals. You add square roots of rational functions and not just square roots, any kind of roots and so forth. Not just roots, of course. So, okay, so you look at this thing, and again, you should think of alpha, beta, and gamma coming from this algebraic closure of f of Y. And if you look at this, then we are kind of lucky enough that x squared has 0 coefficient here. And so this means that the coefficient of x squared here is also 0, but the coefficient of x squared here is minus of alpha plus beta plus gamma. And so this means that alpha plus beta equals minus gamma. So we know one thing about alpha, beta, and gamma, which is this thing. I mean, I don't know alpha, beta, and gamma. We need to solve this equation over f of y. But like finding something in the algebraic closure of f of y. But I do know this. So, and we also know that L, that's something that we talked about before, L is isomorphic to K of alpha, right? Because dividing by the polynomial is isomorphic to saying adjoining one of the roots of this irreducible polynomial. So L is K of alpha essentially. And if L, I mean, for L to be normal over K, what we really need, and that's sufficient and necessary, is that beta will be in K of alpha. Right? Because if beta is not in K of alpha, then that's not a normal extension. L is not a normal extension because one of the conjugates of alpha doesn't sit in K of alpha. And L is isomorphic to K of alpha. And if it is, then beta appears already in K of alpha, and therefore, because of that relation between gamma, alpha, and beta, also gamma. Right? So if this is a normal extension, so if beta is contained in K of alpha, then that's a normal extension because beta and therefore also gamma is in K of alpha, which is isomorphic to L. And if beta is not in K of alpha, then it's impossible that this will be a normal extension because you are missing a root. Okay. Good. So the question about the normality of L over K becomes a question, like an arithmetic question about whether beta is in like a field theoretic, simple like questions about whether this element appears in this field. Okay. So now let's compare the free coefficients in order to answer this question. So the free coefficient here is minus y squared, and the free coefficient here is the product minus the product of alpha, beta, gamma. So we know that alpha, beta, gamma is y squared, and we also know that gamma is minus the sum of alpha and beta. So plugging it here, you get this equation. Right, and you should think of y as something simple and alpha and beta as something complicated, right? Because alpha and beta come from the algebraic closure of f of y. And this is an element in f of y, like the rational function field, even the polynomial ring. Okay, so when we divide by alpha, alpha is not 0. When we divide by alpha and open things up, we see that saying this is the same as saying that beta squared plus alpha beta plus y squared over alpha is 0. And we kind of want to understand whether beta is in K of alpha. So let's express beta in terms of alpha and the y's. So, solving this quadratic equation, and I'm assuming a characteristic that's not 2 for now, then beta is minus alpha plus minus the square root. This is the discriminant here over 2. And I'm kind of cleaning up this discriminant. I'm kind of dividing by 1 over alpha and multiplying by alpha. And then the product of alpha, the alpha factor here, it gets inside the square root as an alpha squared. And if you look at it for a second, this is the same expression. And the way I did that, I divided by 1 over alpha and multiplied by alpha is because I wanted to see alpha cube here. Because alpha cube, we know it's y squared minus alpha, right? Because alpha satisfies this equation. Right, alpha squared plus alpha is y squared. So you can replace this alpha squared by this expression, and then the question of whether beta is in K of alpha boils down to the question of whether this square root, when you plug this instead of alpha cubed, which is this thing, is also in K of alpha. Right, so that's really a more arithmetic question now, whether this expression is in K of alpha. And that's the condition for normality here. Good. So to recap, L over K is normal if and only if we have this containment. So let's see. And it gets kind of slightly involved technically, but I think it's a good thing to see and kind of doing the abstract also in an example and see what what's going on here, and also later on appreciate all the results, the general results that you will have that will save you from doing all of these things. So, right, so I could have used things I know that we'll see, but I obviously I decided not to, and I wanted to do it by hand. So for this square root of these elements to be in K of alpha, I mean, what's K of alpha? So as a vector space over K, because it's a degree 3 extension, you can write it as some A plus B alpha plus C alpha squared, because, you know, 1 alpha and alpha squared are linearly independent over K. So this is also a vector space over K of dimension 3 with basis 1 alpha alpha squared, basic result, right? Because if there were a linear combination of these, then the polynomial equation, then the reducible polynomial of alpha would have been of degree 2 and not 3. So we know that. And so we know that if this element appears here, then you can write it as A plus B alpha plus C alpha squared, where A, B, and C are rational functions in Y. Right? Because K is, if you remember, K is f of Y, the rational function field. And so, okay, so if you take a power of 2 on both sides, then on the one side you'll get this expression. And on the other side, well, you need to take this to the power of 2, and also modding out by alpha cubed equals y squared minus alpha. And if you do it carefully, you will get the square of this is this thing. Right? So I wrote the coefficients of alpha 0, alpha to the 1, alpha squared. Right? So the free coefficient in terms of alpha turns out to be a squared plus 2bc y squared. That's not hard to see. A squared is, you multiply this by itself. And the 2bc comes because of the modding out by alpha cubed. So we need to do it a little bit for a second, but trust me. I double checked. And the coefficient of alpha is this expression, you know, 2b times a minus c plus c squared y squared. And the coefficient of alpha squared is this 2ac plus b squared minus c squared. Now, these a, b, and c, generally speaking, are coming from the rational function fields in y. But I claim that from here you can see that these are actually polynomials in y, which is going to make it easier to work with. Because, for example, let's consider the coefficient of alpha squared. So here it's this thing. And the coefficient of alpha squared here, right, the square of that, is minus 1. Right, so you have this. And this forces b squared, c squared, and 2ac. I'm assuming all of the time the characteristic is not 2, by the way, but in this case it doesn't matter. These require these rational functions to be a polynomial each, right? You can verify that easily. Verify that kind of obviously, right? You know, if a over b plus c over d is like these are polynomials. Is another polynomial, then and you made sure that A is coprime with B and C is coprime with D, then it means that B and D are invertible, they're constant. Let me remove that. So anyhow, we know that B squared, C squared, and AC are polynomials, and therefore also B and C are polynomials. But then, so I know that AC is a polynomial, so I don't know, maybe these are rational functions that are inverted of one of another and so forth. But now if I look at the free coefficient, which is this thing, on one hand it's that thing, on the other hand it's 0, because here you have no free coefficient in alpha. So we know that this is 0. But you know that B and C are polynomials. So this means that A squared is not just a rational function, it's really a polynomial. Right? So also A is polynomial, and overall, A, B, and C are all polynomials, as I said. So to recap, we have the following polynomial equations in A, B, and C. And now that I know that they are polynomials, the way I decided to go forward is to look at the degrees. So let's denote by little a, little b, and little c the degrees of capital A, capital M, and capital C. And again, I'm assuming the characteristic is non-zero. It's not 2. So by the first equation, you can see that the degree of twice the degree of A, namely 2 little a, is the degree of this thing. which again, because the characteristic is not zero, so this two doesn't kill this expression. So the degree here is little b plus little c plus 2. Right? So we know that 2a is b plus c plus 2. And what I claim is that actually a and c are the same. So capital A and capital C have the same degree. And the degree is 2 more than the degree of b. So let's see that. So first of all, I'm claiming that a equals c. So let's assume that c is larger than a. Okay, and now if you look at the second equation, under this assumption that c is larger than a, so that's the second equation. So let's write it here. So this means because c is larger than a, then we know that the degree of this is actually c, right? Because a cannot possibly affect the degree when the degree of a is smaller than the degree of c. And so the degree on the left-hand side, on the right-hand side, sorry, is b plus c, because of this b, and this 2 doesn't matter, because the characteristic is not 2. And on the other hand, the degree here is, well, it's 2c plus 2, degree in y form. So we know that 2c plus 2 equals b plus c, so that's what I written here. 2c plus 2 is b plus c, right? Same thing, good, yeah. Which means that, moving things around, which means that b is c plus 2. And now, if you remember, we also have the 2a is b plus c plus 2. So if you plug b here, right, so you put this c plus 2 here, when you see that 2a is actually 2c plus 4, right? These two c's and these 4. So in particular, a is larger than c, which contradicts the assumption that c is larger than a. So it can be the case that c is larger than a to begin with. So let's assume that c is smaller than a, right? And now let's look at the third equation. So you look at this equation now. So maybe let's erase those. And now we're looking at this equation, which I think I actually wrote here, and I'm rearranging it, right? So sorry for moving back and forth. So you look at this equation, you move things around, so you get that b squared plus 1 is c minus 2a, right? You just need to like subtract another c squared and add the c squared and so forth. But you do that. And looking at that, you can see that, well, the degree on this side is 2 little b, and the degree on that side, because the degree of a is denominating 1 and 2 is non-zero, then the degree of this is actually a, and the degree of this is c, right? Again, because a is larger than c, so the degree of this is a. So you get the 2b is c plus a. But we also know that from the previous equation, also used here, the 2a is b plus c plus 2. And so together you get, if you kind of eliminate b, you get that 3 times the difference between a and c is 4, which is impossible because that's a whole number. Good. So you see, I mean, it was kind of an ad hoc calculation that showed us that a equals c. And once we know that a equals c, again using this equation, equation 1, you get that a is b plus 2. Because one of them cancels. Good. So we just proved this claim in characteristic not 2, that a is c and both of them are b plus 2. And so let's move on. So now let's consider again the equations in the polynomials, not just the degrees, because I want to play with them a little bit and then go back to the degrees. So we had this equation before. I think it's the third equation. Yeah, and I'm adding and subtracting c squared or 2c squared in order to write it as such, as 2ca minus c. So you see here you have like minus 2c squared. So I'm adding a 1c squared to cancel out and get the original one, plus a b squared. And I'm multiplying this by b. So we get that minus b is 2bc times a minus c, plus b times this expression. So we have this thing from the third equation. And now let's consider the second equation, this one. It also has this b times c minus a here, which I deliberately try to get to here. So this is the second equation that we had before, and I'm multiplying it by c so that I can get an expression that looks like that, and then eliminate. So we get that c times that equals c times that. And now, these two expressions are the same, right? Well, they're actually negative. One is the negative of the other, but they're the same up to that. And so when I plug it here and move things around, you get that this thing is b times b squared plus c squared plus 1. Right? This minus b, when it moves to the other side, it gets to this plus 1. Okay, so I wrote it here again. And now let's look at the degrees now. So by claim 5, I know that c is b plus 2, which is in particular larger than b. That's what I need here for this point. C is larger than b. And so if I take degrees, I know that here, the degree of c is the dominating one. So if I take degrees, then on the right-hand side, you get b because of that. And because of that, you get 2 c's. And on the left-hand side, you get, 3c plus 2, because c is c squared and a y squared. I'm kind of using like very mildly things like this is not 0 and so forth, but this is not 0 because the degree of c is at least 2 and so forth. But yeah, so I'm kind of hiding these little assumptions that when I look at sum of polynomials where the other polynomial is a constant, then I know that this polynomial is not going to be the 0 polynomial because this is like a real polynomial, it's not a constant. I think I did it maybe before one time also. Okay. But I'm more careful when I have a sum of polynomials, right? So I'm making sure that I know that whose degree is larger and I'm taking that degree into consideration. So in any case, 3c plus 2 is b plus 2c, and that will give you that c is b minus 2. But if you remember, c is b plus 2 by the previous claim, so that's a contradiction. Okay, so by these degree considerations and playing around with the equation, which honestly takes some time to figure out what's the right way of doing it, we figure out that at the end of the day, this extension over k is not normal, at least when the characteristic is not 2. Anyhow, next time, in the next video, I'm going to talk about separable extensions. In our case, unlike usually in Galois theory, separability is an issue because usually in Galois theory, you work with characteristic 0 and everything is separable and nice. And in characteristic which is positive, which is our case, then the extensions may not be separable. In fact, if you extend finite fields and you look at finite extensions, then they are separable. These are called perfect fields, but it's part of perfect fields. But we will also extend infinite fields, like the rational function field over F5, right? So these extensions may not be separable, and we will actually need to work slightly in order to kind of break down a general extension to its separable part and the so-called purely inseparable part and so forth. So that will require some work, which usually you don't see in Galois theory. So what I'm doing here in the next video, I'm doing the basics of separable extension, which you probably have seen. And the extras that we are going to need, I'm going to put in videos which are not addendum to the course, they're actually part of the course. Okay, hopefully this was helpful. And again, you should look at Richard Borcherd's excellent videos in this Galois theory course that he has, and all our courses really.